I think, yes. Welcome to a special summer session of our series. I would say the Defining Cognitive Science series, but it's actually a bit more than that. It's cognitive science, and I'm the director of cognitive science. Steve DiPaolo, and cognitive science here at SFU is psychology, computer science, linguistics, and philosophy. But this special event also has quite a strong tie with the philosophy department and the linguistics department. So all three of us are quite honored to have this special guest. And I'm going to have him introduced by his host, Andre Begbie. There you go.
Fine. Begbie?
Begbie, yes.
Thank you.
All right, so it's my great pleasure to introduce Dr. Paul Pietroski, who's a professor of philosophy and linguistics at the University of Maryland. So Paul is a great guest for us because he is a true interdisciplinarian whose work integrates methods and ideas from philosophy, linguistics, psychology, cognitive science into a truly integral whole. So Paul is, among other things, the sole author of 2 monographs, both on Oxford University Press, the most recent of which is Events and Semantic Architecture, which came out in 2005. He is in the process of finishing up a 3rd book to be called Conjoining Meanings, Semantics Without Truth Values, which is based on a lecture series that he gave last year at the Jean-Nicode Center in Paris. He has authored or co-authored a number of important articles that have appeared in venues such as Journal of Experimental Psychology, Cognitive Science, Natural Language Semantics, Mind and Language, Biolinguistics, etc. And among his co-authors, a very impressive list, you'll find people like Robert Berwick, Norbert Hornstein, Stephen Crane, and a certain Noam Chomsky. So, without further ado, please join me in welcoming Dr. Paul Pietroski, who will talk to us about semantic framing, the meaning of most.
Thanks very much for coming on a very nice summer day. So what I'm going to do is talk to you about the some work I've done with some colleagues in Maryland about the meaning of the word most. But I want to get into it by starting by thinking about something that's common for all of us in the cognitive sciences, Kahneman and Tversky. And I think of this idea that, look, if you think in a format, and that means you're going to be subject to framing effects. So familiar to all of us here. The bat and the ball they together cost $1.10, and famously the undergraduates at Stanford and MIT and Harvard blow it, and that tells us something about a certain kind of laziness of thinking we're disposed to fall into. Right, and you give people the sharp hint that 10 cents is not the difference between 10 cents and $1 is probably not $1. Slightly more interesting kind of example, right? Adam and Beth, they're driving these cars, and you ask people who's going to save more gas by going from 12 to 14 or from 30 to 40, and famously people are sure that going from 30 to 40 is going to save more money, but of course you sort of how you could figure this out, but who wants to do all that work. As Kahneman noted in his recent book, it's quite interesting that if you flip it the other way around and ask people how to do this in terms of gallons per miles, people will admit they don't know. We're all familiar with loads of phenomena like this, and all I want to do for today is just to put in your mind the very familiar idea that how you pose a question can, of course, have an effect on how people answer the question. And what we're going to be doing is taking advantage of that basic fact that if you set up your experiments in the right way, then how you pose a question to somebody in terms of, say, how many dots on a screen might reveal to you something about the cognitive format that they use to represent the question and represent possible answers. So although I'm basically a linguist coming at this, I want to ask, so how do people understand the word most? What we're going to be using is methods that trade on framing effects. This work is all done collaboratively with my colleague Jeff Lids in linguistics at Maryland, Justin Halberta at Hopkins, and then, of course, the people that do the real work, the graduate students. And I have to tell you, the worst possible thing that can befall an intellectual project has befallen this project. All the graduate students have gone off now to get jobs. But I will tell you, in particular, Darko Odic is about to be your colleague local colleague at UBC. And he is absolutely fantastic, so I urge you to get to know him when he moves to Vancouver in 2 weeks. So here's a scene you might present to subjects familiar from lots of work in vision science. You have some colored dots, in this case 15, 9 yellow, 6 blue. And one thing you might ask is, are most of the dots blue? And in this case, what we want to do is get at how is that interrogative question understood? That is, what question is getting asked when you pose a question, or most of the dots yellow? And here's to give you a flavor of the kinds of possible answers one could give to that question. Well, I say, well, look, most, at least in a language like English, means something like more than half. So here's a hypothesis. When you present to the subject question, most of the dots are yellow, they hear it, so to speak, in their language of thought is yes or no, more than half of the dots are yellow. Another possible way you might imagine the subject could understand that question is, well, is the number of yellow dots bigger than the number of non-yellow dots? Or more than half of the dots yellow, or is the number of yellow dots outnumber the non-yellow dots? It's going to give you the same yes or no answer if you're doing it right. But the first would, so to speak, suggest a computation where you ask is 9 bigger than 15 over 2? Second computation, you compare 9 to 6. Another possible way of thinking about it would be to say, we'll take the number of yellow dots, take the total number of dots, 15 in the scene I showed you, take 15 minus 9 and compare 9 to 15 minus 9. Now, I wouldn't put anything that crazy, of course, unless I was going to tell you, and that's the way we think people are doing it. I'll come back to yet even another possible way of thinking about it. But part of the reason we're interested in this kind of phenomena is that what we've got is a case with a logical vocabulary word like most is various possible ways of thinking about how you might represent the question, and they all turn out to exhibit a certain kind of provable logical equivalent. So you've got a situation where, so to speak, the same situation can not only be described in many ways, but the many ways of describing the situation are from a kind of logical, mathematical perspective equivalent, and so this provides a way of trying to get at what the underlying representational format is. So you could imagine, so to speak, one kind of mind that hears most in that way, another kind of mind that hears most in that way, another kind of mind that hears the most question that way, and they would all, so to speak, give the same answer. And so one question you might ask was, look, do humans all have the same kind of mind in this respect? And I'm going to say yes. The answer turns out to be yes there, too. There's another possible answer, which is one that Jerry Fodor and my friend Ernie Lepore kind of like, which was, well, we have a stunning hypothesis about what the word most means. It means most. Stop, shut up, say no more. And you could imagine that kind of mind, too, where the most is just a sort of a basic atomic expression that just goes for a certain kind of relation that might be exhibited between sets. And then if you know anything about the foundations of arithmetic, in fact, you don't want to know very much about the foundations of arithmetic. Now, actually, there is a way of even answering a most question that wouldn't involve representing numbers at all. So there's this thing called Hume's principle, which is just the very fancy principle that if you have some things, and you have some things, and if they correspond 1 to 1, then the odds are very high that you had the same number of things both times. And so if, in fact, you had a notion of 1-to-1 correspondence, then with the idea of just getting at the idea of a remainder, so 1-to-1 correspondence, and there's one left over, there are various ways of getting at the idea there are more of these than more of these without representing cardinality in the first place. And if you're worried about infinite sets, you can handle them too. And if you weren't worried about infinite sets, good for you. In fact, you can define a notion, if you like, of instead of 1-to-1 correspondence, 1-to-1 with remainder. So you could imagine a kind of mind that can't represent cardinality at all, but it can represent one-to-one correspondence and leftovers. And it, so to speak, could give the same answer, same yes-no profile of answers to a question, are most of the dots yellow, as could your atomic mind that just says, oh, I've got it. I've got the most relation. I've got a word for that. And then minds that engage in various kinds of computations. And if you think about mapping out these various possibilities, they kind of fall into an interesting, you can map them out in various ways, but there's the, so to speak, the one-to-one plus idea, which you can think of over there in numberless land, right? I could give you the idea of there are more than these than more of those without doing anything about numbers at all. Or you could imagine various minds that deploy number representations, but their number representations hook up with the word most in different ways. So one kind of mind that, so to speak, hooks their word most up with a notion of conjunction and a notion of half or something like that. Another kind of mind that represents their notion of hooks up their notion of most with a notion of number and a notion of conjunction, and crucially, a notion of negation. Right, so most of the dots are yellow for such a mind might mean the number of yellow dots is bigger than the number of non-yellow dots. So you take your predicate yellow, make up the predicate non-yellow, and understand most in that way. This way of doing it, you say, nah, we don't need to use any kind of turning yellow into non-yellow. We'll really, really push our representations of number with a vengeance, and we'll say, I'll represent the number of yellow dots, the number of dots, represent the number of yellow dots, and then actually do cardinality subtraction. So for those of you that know a little bit of logic, I think, geez, how could you possibly could there be any possible bite to a distinction between predicate negation and cardinality subtraction? Part of what I'm going to be suggesting is yes. For those of you that come from animal psychology work and are thinking to yourself, you know, animals don't like doing negation. I don't think that's going to be the way a good animal would like to think. And if others of you are coming from a logic tradition and thinking, I love my predicate negation, but I'd really like to be able to do one-to-one correspondence without number, right, you will be having, so to speak, several of the same kind of conversations we had around our lab meeting table when I put down a large bet that it was going to come out to be a one-to-one correspondence. And my colleague Justin Halberta said, no, I know animals. They're not going to have anything to do with that. It's not going to be negation. It's going to be something like that. And I had to pay up the bet. And such is life when you try to make these questions empirical. But in any case, what I want to do is walk through a series of experiments our group has done that's led us to think, in fact, that's the way ordinary humans end up representing, and I mean the little ones too, representing the meaning of most. But what I really want to do, I mean, it's not that I care about the word most. I mean, one shouldn't just devote one's life to a lexical item. But what I do think why this is interesting is that what we've got here is a sort of example case study of how what you might describe as a single truth condition, what's the yes-no profile for or most of the dots yellow. And we have these various ways of representing, and at least for finite cases, these four ways of computing the meaning of most are all mathematically equivalent. So for the linguists in the room who are thinking, hey, can we get a case where we could study meaning differences where you get the same mapping from possible worlds to truth values? Well, here we go. And here we get a case study in how to think about what the format for lexical meaning might be, holding the mapping from possible situations to yes-no answers constant. Martin Hockel and colleagues starting at Pomona and now at MIT have, for independent reasons, been interested in the idea that more might mean more than half, and in particular interested in the idea that it doesn't mean more than half. And in the interest of time, I'm not going to review Martin's work or confirmatory work from our lab showing that, in fact, yes, the more than half meaning is not the way to go. If people want to talk about that afterwards, we can. But I'm going to assume that for today, Martin and company have made the, how do you understand the meaning of the word most? Get a division by half operator in there, and that's how you do it. I'm going to set that aside and just focus on the one example of a possible meaning representation that involves no number representation at all, and then how you might choose between two alternatives, both of which involve number representation, but one that involves predicate negation. And you might have thought in terms of lots of animal learning literature, not your best bet if you're a biological creature trying to do this kind of stuff. And another one that involves cardinality subtraction, which you might have thought would just be too computationally difficult, and eventually suggest that that's looking like the answer. In particular, these three have the nice property, I think, of also not being crazy in a certain technical sense. Karen Wynn and her group at Yale have shown that, at least by the age of 6 months, infants actually have quite sophisticated capacities for being able to do one-to-one correspondence. So the circuitry for doing one-to-one correspondence detection there, we know, was at least there in the little humans, and some work suggesting that it's available in other animals. The notion of doing complex computations, even including subtraction. There's a fair amount of works, even amongst stuff that Randy Gallistel has reviewed many times involving insect navigation, suggesting actually, although it might initially sound crazy, having little counters that are keeping track of the values of a variable and then performing computations on them, that seems to be widely available in animal cognition. And at least for humans, having the idea of predicate negation is pretty common. We can say that people are unhappy and not happy and all of that. And so these two pose especially kind of an interesting kind of case study if we're thinking about what drives the interface between the human language system and other cognitive systems. Had it turned out that this was the right answer, then you might have thought, oh, right, there's something really interesting and distinctively linguistic about this, right? The fact that you can have not in a language and create complex negated predicates sort of overrides an animal's general tendency to not want to have to do predicate negation. On the other hand, if this turns out to be the answer, then you might think, well, okay, maybe what's driving the interface between pre-linguistic conceptual systems and these meaning representations we form up is, well, look, maybe you actually do the complex computation in order to avoid having to do things like predicate negation. If people know about working vision scientists, you'll know the vision system very good at yanking out like how many red things there are in a scene, not so good at yanking out how many non-red things there are in a scene. That'll be crucial with regard to one of the experiments. In any case, that's really why I'm interested in this, is really as a kind of case study for thinking about representational format in a domain where, in fact, all the formats are actually viable candidates. I think you could have imagined a natural history where any one of them turned out to be perfectly reasonable. Okay. If there's time at the end, I'm going to come back to most of the paint is yellow. Linguists in the room may be already thinking, most of the dots, I can see how you do that in terms of cardinality. How are you going to do it with stuff? And we're just moving into that in our group, but I'll hopefully end with an experiment how to extend this to the mass noun case. Until I come to the end, though, everything I'm going to be talking about is going to sentences of the form most, plural count noun, dots for these experiments, and then a color term, either yellow or blue. I'll just say very briefly, my guess is for a cognitive science audience, not much is needed to motivate the idea that most is not just a primitive expression that just means most, end of story. But just to remind you, if you've got your Jerry Fodor, I'd really like everything to be atomic, no decomposition, that makes me upset. Just remember, we're talking about the logical vocabulary here. So I don't think words like dog and cat have any kind of interesting decompositional analysis. But the logical vocabulary really does seem to be special, and special precisely because, surprisingly enough, there seems to be logical relations amongst the logical vocabulary items. So famously, words like some and none, we know there are characteristic entailment patterns. If some of the yellow dogs barked, then some of the dogs barked, but not vice versa. If none of the yellow dogs barked, well, it doesn't follow that none of the dogs barked, but if none of the dogs barked, none of the yellow dogs barked. So it's we can map out which way entailment relations go with words like some and none, and that sort of makes you think, maybe some and none are not just atomic expressions that have nothing to do with one another. Maybe they fit as part of a larger logical pattern. And most, it turns out to be, in fact, fantastically interesting with regard to its pattern of entailments. So while there's no inference from most of the yellow dogs barked to most of the dogs barked, could have been that most of the yellow ones did, but most of the dogs didn't. If most of the dogs barked loudly, it does follow that most of the dogs barked. And there's a whole, actually, network of interesting relations that show that most is in some ways unlike the classic Aristotelian troika, every some no, but it's not out there just completely completely on its own as unrelated. If I had much longer, I would tell you lots about the logical properties of the word most. But that's going to be basically my reason for thinking there's something interesting going on here. And if you think about it, even most doesn't have to mean more than half for you to know. Geez, if most of the dots are yellow, I guess more than half of the dots are yellow, which suggests there's relations between most and more. That's hardly surprising when you think about it. But the idea that most is just sitting there in atom, I'm going to set that aside. And so get rid of that. Assume that Martin Haeckel has shown us that we don't at least analyze most as more than half. And now think in a little more detail about that first idea. Look, maybe there's no number representation at all. You could easily imagine a child being introduced to the word most in kind of canonical situations, and some sense sort of recognizing that you have the one-to-one correspondence with remainder relation, and maybe that's how they understand the word. So what we wanted to do was see if we could find some evidence, something like a framing effect, suggesting that that's not how people were understanding that question. And here's going to be the driving idea behind all the experiments I'm about to tell you about. We want to do is ask what conditions make the question either easy or hard to answer. The idea being that might provide clues about how the sentence is understood if you've got a decent account about the information that's available to people in those conditions. Now, what's going to be crucial is you've got to have a decent account of the information available, but bless these vision scientists, if all you do is present people with colored dots for 200 milliseconds, they have exquisite models about the information that's available. So what we're going to be doing is using off-the-shelf methods from vision scientists where there are well-understood psychophysical models, put subjects in the unnatural situation of having to answer the question, or most of the dots say yellow, in about 200 milliseconds, because in that window we have a pretty good idea of the information available to them. And then we're going to try to then use that to say, okay, given the information you have available, can we now manipulate what you look at in a way to show, oh, you're really good at this, you stink at this, maybe now that tells us something about how you're understanding the question. I'll assume in this audience, I don't need to give a big review about the approximate number system, but just as a reminder, there's this ancient cognitive system that we share with rats and pigeons and all sorts of animals about how to make a guesstimate of how many objects there are in a field. So if you just look very fast at how many chairs there are up front and ask people to just, you get a snapshot, people would be guessing 5, 6, or 7. If I present an array of 50 dots for a brief period and ask people how many dots are there, people are going to offer answers like 44, 53. And the crucial feature of this system, and it's all that's going to matter for these purposes, is that this system allows you to provide ratio-dependent estimates of the object you're looking at. So all these curves there just representing the fact that if, so to speak, there's 12 objects, you're going to sometimes you'll sometimes think they're 11, sometimes 13, but you'll guess 11 and 13 more than you would guess 10 or 14, which is more than you would guess 9 or 15. And crucially, distinguishing 16 from 8, you'll be exactly as good at that as you would be from distinguishing 8 from 4, 64 from 32. So what you've got is this capacity to make estimates of how many things there are as long as they correspond to a detectable visual feature, though it's not just vision, right? If you think about how many times to tap your finger about 17 times, people's responses will be a normal distribution around 17, right? Stan DeHane's the number sense is the go-to introductory discussion of this. I'm going to just take it as a given that humans, like other animals, can do this. In fact, infants are pretty good at actually making discriminations in the 2-to-1 kind of ratio. For humans who don't undergo the kind of training that a pigeon undergoes, we start our performance really starts deteriorating when you hit 7-to-6, 8-to-7 ratio. Put a pigeon through the mill, they can get really, really good at this. But all of our experiments are basically going to top out at 8-to-7, 9-to-8 ratios. So that's, again, the key thing. And it feels intuitively right, and it is right. Distinguishing 8 from 4 is easier than distinguishing 10 from 8. And if you don't know this literature, that's really the only fact you've got to tuck away for what I'm going to say next. So correlatively, as the number of dots rises, your acuity, so to speak, is going to go down. I mean, even if you show people 101 dots and ask them how many there are, get enough people guessing, and you'll still get a normal distribution around 101. This is the why the jelly bean phenomenon at the circus works, right? You know, if you just take a guesstimate to get large numbers of people guessing, you'll as a collective zone in on the right answer. But for any individual, your acuity is going to decrease, right? So if there's 54 dots, you're not going to nail it as 54 very often. Okay, so back to what conditions make the question hard or easy to answer. So at 200 milliseconds, not enough time to count. 4 to 5 is, a medium hard ratio, though people get very good at this. Just a few practice trials, and people are just shouting out yes, no, and they're actually really get quite good at it. 1 to 2, super easy ratio. That's a different kind of stimulus, which I'll come back to in a minute. There's a 9 to 10 ratio. That one's pretty hard. There's a different kind of 4 to 5 ratio that you might wonder, I bet you could make answer how many are there more yellow dots than blue ones on that one pretty easily. There's a different kind of possible stimulus you could have with a 4 to 5 ratio or a 5 to 4 ratio. And here's the idea behind the first couple of experiments. We had 4 trial types. One trial type up there called, for the obvious reasons, scattered random. Another trial type, scattered pairs. Another trial type called column pairs mixed. And then this trial type called column pairs sorted. Column pairs sorted is in there to have some easy trials for subjects, because subjects have to do like 300, 400 of these, and they breathe easy when that one comes along. But what we also wanted was a trial type where, so to speak, a known cheat could be used. So you could basically be answering the question on the basis of line length, because we wanted to show there's nothing about our experimental setup that just forces people to lock onto a single method. When people can use a cheat like line length, they will. The interesting thing for us is going to be the other 3 trial types. And as you might guess, that trial type you might have intuitively thought is, well, look, if I'm looking for one-to-one correspondence with remainder, that should be a way easier trial type to deal with than that one. Whereas if I was just doing thing on taking guesstimates of how many dots there are, that one shouldn't make any difference. That one you might wonder. I mean, there is a certain sense in which there are 2 yellow dots just sitting there with no teammates, but for most of us, that's just like, please don't make me look at that trial type. It sort of hurts. But in any case, our thought was we just wanted to see if when you ask people, are most of the dots yellow, do you get any differences across these trial types? And if you don't, how well does a known psychophysical model of the approximate number system accommodate data for all 3 of those trial types? So here's your basic design. Take some undergraduates either at Maryland or Hopkins, 360 trials for every participant, ranging from 5 to 17 dots. The trials vary from the really easy ratios, 1 to 2, to the really hard ratios, 9 to 10. They look for about 200, for exactly 200 milliseconds. They get to see it, and then they just have to push a button saying yes or no to the target sentence, which most of the dots are yellow. The correct answer is randomized. You got to control for like the spread on the scene. So we have controlled to make sure that it's not number of pixels that they're responding to. And if you know how to have these experiments run, there's 24 things you've got to control for. But this is why Justin Hilberta is part of the team. But if people want to talk about the details, we can. Here's the here's the punchline. That one over there is the only oddball. Subjects treated the other 3 kinds of scenes exactly as if they didn't care about the spread or arrangement of the dots, and as if the only thing they cared about was their capacity to do a guesstimate of how many yellow dots there were. So that line at the top with the insanely good performance, 95%, regardless of ratio. That's the yellow line is just longer than the blue line, right? So that's the oddball performance, the one there at the top. So what you're looking in the left column is percentage of cases correct. So in the super hard ratios on the other three trial types, you can see you're asymptoting down to about 50% plus 1. And what you're looking at here is the ratio. So here your super easy ratio of 2 to 1, and over here your super hard ratio. So when you just give people the sorted columns, they're just like almost at ceiling, 95% regardless of ratio. For the other three trial types, right, 1, 2, 3 trial types, what you get is this characteristic phenomena of the approximate number system, namely ratio dependence. So, okay, what we were able to show was you get ratio-dependent responses in all the other three trial types. But far more interesting, there are independent, not from our lab, a psychophysical model of what you should expect the response to trials like this to be if people are relying on the approximate number system. So there's a psychophysical model of, so to speak, what the behavioral response of the approximate number system is. So what we did was just take that model and now use our data and do the R-squareds. And what you can see is that on the three trial types that were of interest to us, you're getting very good fit between the model of what the behavior should look like if people were using their approximate number system and what their behavior actually looked like. And on the, there's also a psychophysical model of what you should be doing if you were doing the line length kind of thing, and got a good fit there as well. So not by any means anything decisive yet, but you might have thought that if you did understand the question most in terms of one-to-one correspondence, you might have expected to find better performance there than there, and you certainly wouldn't predict that if what you're trying to answer is a one-to-one question, that the fit between your performance on those trials and the approximate number system would be as good as it was. Now, there's a possible response, which is, okay, 200 milliseconds is just not enough to do your one-to-one detection. It is enough time to do your approximate number system, not enough time to do a one-to-one correspondence, so people just had to fall back on whatever they could use in this window. So we did the obvious thing, take the scatter pair trials now, take a different group of subjects, and just see how well they can do on that trial type when you pose the question differently. So when you ask them questions like, did you notice if there were any outlier dots? And if you did, can you tell me what color they were? Or questions like, can you tell me what color the outlier dots were? So a whole bunch of different kinds of questions that get at, could you in fact have done this by a one-to-one kind of way? And let's up the ante. Let's only give subjects 150 milliseconds to do that. And the answer is, not only can they do it, their performance was better than if you give them 200 milliseconds and pose the question as a most question. So what you're looking at here is here's a curve that was describing performance on the original scattered dots trial, where the question is posed as a most question, and they get 200 milliseconds. And here's questions of the other sort, like, did you notice that there were outliers? Could you give me the color of the other outliers? And in fact, people's performance was better on those tasks. So it certainly doesn't look like it doesn't look like the 200 millisecond window forced people into not using the capacities that they've got for doing one-to-one correspondence with remainder strategy. You just had to pose the question in a way that made them not use those capacities. And that led us to think that the word most is like a way of getting people to not use those capacities that they've actually got. though, right, one experiment, still just one. And the next experiment I'm going to tell you, which is really designed to test between those, includes a replication of the initial study in a slightly different context. And I can tell you now that other labs have replicated everything I'm going to tell you about in Polish. So Polish blissfully has a quantificational word just like most, and these studies have now been replicated in another lab in another language. But that first study at least did suggest that prima facie, posing the question with most is not a way of posing a one-to-one plus question. So if we set that aside for just a moment, and now say, well, look, so maybe framing the question with most has effects that are better understood in terms of cardinality comparison. A next kind of question you'd like to ask is, well, what kind of cardinality comparison? Are you doing comparing the number of yellow dots to the number of non-yellow dots, or are you comparing the number of yellow dots to something that whose answer you compute, let's say, by taking the number of dots and subtracting the number of yellow dots? So we're going to shift to experiments using multiple colors to answer this question. So we still want to ask for a question that I'll say, like most of the dots blue, what conditions make the question easy or hard to answer? And you can imagine making the question easier or hard to answer by holding the total number of dots fixed, but changing the number of alternative colors. So now the question, are most of the dots blue? And in fact, you might ask the question, are most of the dots blue in a 2-color case, 3-color case, 4-color case, or 5-color case? So what you're doing is amping up the number of non-blue colors. And here's the key background fact to this. While the visual system is quite good at giving you an estimate when you're presented with a scene of the total number of dots, whether it doesn't matter whether you like it or not. Present dots, the visual system will go boom, about 34. If there are 2 colors, the visual system says, great, I'm really good at giving you an estimate of subsets. They'll do reds, blues. But of course, if there were 37 colors, your poor little visual system and memory resources start giving out. For most of us, 3 is about the number of estimates you can hold in mind at any one time. Some people look like they can do 4 a little bit some of the time. 5 seems to be beyond the normal human pale. So given that background fact, if you had a 2-color scene, there's a nice, easy way to do it if you're faced with the question, how do I figure out who the non-blue dots are? The visual system, so to speak, can't see things as non-blue. But if you just have blues and reds, the reds serve as a pretty good proxy for the non-blues. On the other hand, if you've got blues and reds and greens and yellows, now it gets harder to get a proxy for the non-blues. And since there's independent evidence that you're going to use, so to speak, one of your slots to take an estimate of the total cardinality of dots, for most of us, total cardinality dots, reds, and now one other color is going to be about the most we can hold in mind. So as you add colors, this strategy of how am I going to figure out the blues? Well, I'll take how am I going to figure out the non-blues? Well, those are just the reds. That strategy will start giving out, because if I give you 5 colors, you say, great, I got the total number of dots, I got the blue dots. Now how do I figure out what the non-blue dots are? That would be the sum of the greens and the yellows and the oranges, and that the visual system can't do for you. So here's the thought. If, in fact, you understood the meaning of most of the dots are blue as the number of dots is bigger than the number of non-blue dots, then your performance should be pretty good in the 2-color case, start to get worse in the 3 and 4, and by the time you get to the 5-color case, you should just stink at this. By contrast, if you were doing the cardinality subtraction algorithm, the cardinality subtraction algorithm doesn't care how many non-blue colors there are, because you're taking the number of blue dots and taking the total number of dots and then just figuring out the right side of the inequality sign by doing a computation. There's also another way you can tease these 2 hypotheses apart, because the first hypothesis has you comparing 15 to 9. So if you got 15 dots, 9 are blue, 6 are red, you're really comparing 9 to 6. This computationally more complex proposal has you actually comparing 15 to 6. But you're doing it by you have to take an estimate of 15 and an estimate of 9. So here, the system would be taking estimates of 9 and 6. That predicts a certain kind of relatively narrow normal distribution. Comparing 15 to 9, well, actually, now you're into a larger error range. So actually, although your performance should be decreasing as you go from 2 colors, 3 colors to 4 colors to 5, when you're in the 2-color case, your acuity, your estimate, should actually be relatively tight and pretty good. In this situation, you're predicting indifference to the number of non-blue colors, but predicting that regardless of how many colors there are, your acuity is actually going to be a little worse than it is here because you're forced to take estimates of higher numbers. Now, it'd be really dumb for me to have told you that and then say, oh, and that's not what the experiment showed. Right? So, in fact, right, so that's just making the point, right? So the comparison between 6 and 9, you're using your approximate number system in a good range. You're comparing 9 to 15, you're using your approximate system in a less acuity range. Right, so here's now the facts. You get better performance on the easier ratios, again, replicating the original study, but crucially, absolutely no effect of the number of colors. Whether it's 3, 4, or 5 subjects' performance was the same with an insanely good fit to the psychophysical model. So here it just looked like, okay, fine, multiple colors, just let the approximate number system drive everything. And in fact, the acuities, for those of you that know this literature, you'll know, and for the rest of you, I'll just have to ask you to trust me for this slide. Those acuities are the acuities of what you would get for comparing 15 to 9 and not 9 to 6. So both halves of the prediction seem to pan out. Again, right, never conclude anything on the basis of one experiment. But what I do want to suggest is that there's a kind of strategy for how to pursue this work now in more detail. If you're thinking about, you can compare non-cardinality comparisons like one-to-one plus computations versus cardinality by asking, well, let's play with the stimulus and give subjects ones where it'd be really easy to do one-to-one correspondence and see if that helps them. But then there's this other way of changing the stimulus, which is to amp up the numbers of colors. And I think in general, for thinking about the meanings of logical vocabulary questions, right, that's a potential way forward to try to create stimuli such you can imagine amping up the difficulty along various dimensions. And if your friends, be they in vision sciences or wherever, actually have a model of the information that's available within a window, then you can really do something, right? So for those of us in linguistics, we know we're forever trying to figure out what the meaning is, expression is, by take a situation where the subject gets to think about whatever they like in a very, very complex situation and just ask them yes or no. Hard to get much out of that. On the other hand, if you can find a little window where you actually know something about the information that's available to the subject, now playing with the question is a much finer-grained tool, of course. Okay, I got my signal. So what I want to do is just point at a place where we've been moving lately, which is to see how to get this past doing count nouns and think about things like, is most of the paint blue? Is most of the goo blue? It had been known that other primates have an approximate area system. Hadn't been shown for humans. So, okay, first just go off and show that humans have got it. That's relatively easy. But then what we discovered, let me just get to the punchline here, is that in fact, if you present people with stimuli and you ask them, is most of the goo blue or is most of the paint blue, we're going to do peas and corn in the fall. But people's acuity for the mass noun case is actually a little better. So if you're estimating area, your acuity is slightly better than for estimating count, and that's consistent with the animal literature. So that made it possible to test this hypothesis that's everywhere in the semantics literature. How do you do mass? Well, you do it like with count plus a grid. Of course, if it's count plus a grid, that predicts that actually your performance in the mass noun case should be a little worse because you have to do everything you do in the count noun case and then layer this grid on and figure out what your size is, and there's going to be noise to the edges. So now there's an obvious kind of Kahneman-Tversky thing to do here. try presenting a single stimulus, describe it in two different ways, and see if you can actually show an effect. And so we've done this with a kind of stimulus that can be described to one group of subjects by saying, you're going to see a bunch of blobs, and I want you to tell me are most of the blobs blue or yellow. Another group of subjects gets the question, you're going to see there was this goo, and it went kaboom. And what I want you to do is just tell me, was most of the blob blue or yellow? But the stimulus is the same, and what you get is for the group of subjects that had the question posed in the mass noun way, they show the better acuity than for the subjects that were presented with the count noun question. As if just frame it as a count noun question and you go reach for your, do the comparison that you do for counting. And that one just turns out to be a little less good than the one you do for area. Now, if that holds up for peas and corn, if you could just show a stimulus and ask the kids, are most of the peas blue? Is most of the corn blue? And we're pursuing independent work developmentally with kids. If that would hold up, then that would then suggest that right down to the mass count morphology, you're tapping into related but slightly different systems. If people want to ask questions about about the same kind of stuff but done where you're not doing it at 200 milliseconds with slides, we can talk in the question period. But I'll just stop there. Thanks.
Thank you. It was really interesting talk. I had a linguistic question. Mm-hmm. So with questions like, are most blue dots blue? So could you make an argument that people are not using this predicate negation, using some sort of like reference or anaphoric reference to this what's it called, non-yellow dots? Or
yeah, I hesitate to say anything about what people are doing in actual episodes of like understanding a sentence in a context, right? So I absolutely don't think that people go through the process of doing this calculation and computation in lots of normal cases. That is, often when you want to answer the question, are most of these things green, if you ever find yourself wanting to answer that question, you use whatever method is available at hand. And for many purposes, doing a one-to-one correspondence text is exactly the right thing to do. So this is fundamentally, we're making a claim about what your base level representation of the meaning of most is. Now, as a clever person, you will know that no matter how the question is formatted, there are many ways of getting the question answered. I mean, after all, there's a very easy way, if your eyes are closed, of getting the question answered, or most of the dots yellow or blue. Ask your friend whose eyes are open. Right? So there are going to be all sorts of things one might do in a particular situation about getting the question answered. And about that, part of the reason I like looking at 200 milliseconds when you know the subject has this information and no others, you can answer it. Now, another complication to your question is that lots and lots of natural uses of most or the X's, Y, as you know, have a kind of generic flavor to them. So that in fact, the question you're actually being posed and trying to answer is some kind of just generalization question. It's like, are most swans white, or whatever. And that now spins us off into yet some other related, though independent meaning of most. And we're trying to sneak up on generics. But what we were at least able to show independently is that if you present people with a very specific context with an exact number of objects there, the generic stuff goes away. You really do get to something like a 50% plus one truth condition. But now, even if we're right about what the basic linguistic knowledge is, how do you apply it in an actual episode of linguistic communication? I'm afraid I got nothing on that.
If you change all, for the same pattern, you change all the yellows to blue and blues to yellow and ask, are most blue, do you get the same answer? Just flip all the colors and flip the question.
Yeah. So I've shown you things just with yellow blues or red blue dots because that's the standard kind of vision paradigm. When we do things with the little kids in the lab, it's bananas and monkeys or oranges, and it just doesn't matter. It has to do with it's just like whatever the numerosities are.
Okay, but just wondered because we have blue. Pure blue cones, if you want to call them that. So you've got a different resolution. Just
so amongst the gazillion things you've got to control for, but the direct answer to your question is yes. Just flip the colors; it makes absolutely no difference. Difference.
And so you're saying you've also done it with lots of other stimuli. So if you do it with squares and circles, you get the same.
Yeah, as long as it's a stimulus of the sort the vision system can pick up on it, right? So now you can't do it with like our most democracies, right?
Sure.
But as long as it's sensitive to visual cue, then you can do it. So you can do we've done it with line orientations. So most of them left or right, and it's got yeah.
So this is a little further afield. With respect to people who come from a language that doesn't have most in it, do they tend to, say, have a more difficult time picking up on the meaning or the way in which it's actually deployed?
Yeah.
You were speaking about this in terms of this being one of a key logical term, and I'm thinking, with respect to teaching logic to people who don't have English as a first language, is this the sort of thing where a framing effect might make it easier or harder on undergrads?
Well, I mentioned the replication in Polish because Polish and Hindi are two languages I know about where you at least have a word, quantificational word like most, so you can get most, plural, count, noun, and then predicate, and it has the more than half interpretation. Lots and lots of languages, in fact, most languages are not like that. So a very standard pattern is to get what you get in Romance, where you have a kind of pour la plupart construction. So you can have 10 things, 4 are red, 3 are yellow, 3 are blue, and you say basically more blue than any other alternative. So one thing you have to be just really careful about is just like who gets translated as most. However, we've got a whole bunch of other work that is in the same vicinity, not doing it with most at all, but doing it with more. And at least so far as I know, every language has some version of more. And we're pushing this off into now comparative morphology, so the red lines are longer than the blue ones. But in fact, so there are huge complications surrounding the word most. And so you might say, well, God, so why on earth did you guys start with that one? The reason is because the peculiarities of English, which you can think of as basically giving you a case where this alternative is more than all the others, but here's the one really clean alternative, not blue. So I suspect what's going on in English is that most of the dots are red. Really is, there are more red dots than any other alternative. But quirks of the English determiner system, which are evidently also quirks of the Polish system and the Hindi determiner system, give you a very special way of focusing on where there's only one contrast class. That makes it possible to line up cardinality subtraction against predicate negation as a competitor. So English was great for asking the question, is it predicate negation or cardinality comparison? Now, usual thing, English will not be a great language for asking some other questions.
Most of the questions are coming from first row.
Yeah.
So you were talking about mass nouns at the end. I didn't quite understand what you were trying to say. That they do the performance does improve. So you're saying that they're not using cardinality based system or something.
Well, yeah.
else?
So if you think about it from a just semanticist point of view, what you'd really like is for every predicate in the language to be a mapping from a countable domain of objects into yes or no. So most of the dots red, good, give me the set of red dots, I can take their cardinality. Now we say, what about most of the paint is blue? So, well, what am I supposed to do with paint? Well, one thought is we'll force something like a cardinality onto paint by saying you've got to do it with paint units, right? And there are lots of ideas in the literature about that. So you treat most of the paint as blue as something like fix on an arbitrary unit. Most paint units are blue units. if that's, I mean, I've never believed that for a minute, but if that was right, what you then predict is that people should be a little worse at answering, is most of the paint blue than are most of the dots blue? Because to answer is most of the paint blue, you have to do everything you have to do for or most of the dots blue, plus lay down the grid. There's going to be slippage and error. But in fact, what we find is that when you hold the stimulus fixed, so in that stimulate condition where you can either pose the question, are most of the blobs blue, or was most of the blob blue before it went kaboom? So in principle, you can get people to do a kind of area Massey question or a county cardinality question. What we find is their performance is that dashed line, so their performance is better, so their acuity is, so the W, think of W as like a golf score. The lower number, the better your acuity. And again, you're getting these insanely good fits to the psychophysical model. So you know you're using these two approximate systems, and it turns out the area system is just a little better. Now, as a professional compositional semantics, this means I'm back to the drawing board on how to understand the meaning of paint and blue. Because it's not just about paint. We could have said, are most of the dots blue, or is most of the paint blue? So now our question is about blue. So when your local village semanticist says, I'll tell you what the meaning of blue is, it's lambda x, take x to truth just in case x is blue. If there was a set of blue things that has a cardinality, you should ask your local semanticist, and what is this set of blue things? So I think part of what this shows is that we should be going back to the drawing board and scratch a syntactician, and they will tell you, my guess is that the mass is the nice simple thing, and you add a count feature, right? That's a pretty standard view about the mass count distinction in the sentence, and I think that's right. So I think what's going on is that the lexical items, when they're presented in their mass form, that's just what they are. We have to understand what the meaning of those is without forcing them to really be count nouns in disguise, because the syntactic evidence is they're not count nouns in disguise, and now I think the psycholinguistic evidence is they're not count nouns in disguise. And so the whole idea of having your entire theory of meaning built around the count noun may have been because Frege was really interested in counting. If you were interested in the foundations of arithmetic, counting seems like a good place to start. It may not be such a good place to start if you want to understand the meaning of paint or the meaning of blue.
So I was just wondering, was there any way for you to kind of track how long it took people to answer? So they see the little thing, and then it goes away, and they just sit there and.
Once they are in the zone, so they have like a maybe 3-minute practice session, and once they get in the zone, they're responding like very, very quick. So we in some of the initial studies we did start recording response times to make sure there was nothing funny going on. And once they're in the zone, there's like half a second, boom.
Mm-hmm. So there's no pattern.
Boom, on to the next one. Now I will tell you, we're trying to do some new work with are most of the red lines are the red lines longer than the others? If you do plurality and comparative in the same sentence, the reaction times go insanely high. 3-4 seconds with competent speakers just staring and not knowing what to say. When I piloted it in one of my classes, one undergraduate said, it was like I forgot what the words mean. Now that I think potentially realised I really want to find out what's going on there. But you got a competent speaker, the sentence is one they perfectly understand, you present a picture to them and they're like, but that's absolutely not what's going on here. After about 3 minutes practice, people just zoom through it, and you'll notice, although we were getting we always get p less than 0.001 for these things. That's with 12 subjects, and that's perfectly standard in a vision experiment. 12 subjects is plenty because everybody's. I mean, this looks like it's just tapping into a hardwired system that we all have in common. And so when you get the crazy reaction times, that's what makes me think, oh, something interesting that we don't understand has come in here. Now, I will be honest, slight difference between University of Maryland and Johns Hopkins students. The Johns Hopkins students take it all a little more seriously.
Please join me in thanking Paul for this fantastic presentation.